So far, we have learned about three formal representations for languages, and they are deterministic finite state automata, non-deterministic finite state automata, and non-deterministic finite state automata with epsilon transitions. And we have proved that all these three are equivalent in power for representing languages, which means each one of them represents the family of regular languages. And today we are going to learn about a new mathematical representation or formal representation for a language, and which is a grammar. And a grammar is a set of rewrite rules representing a language. And to understand how a language is represented by a grammar, let us start with an example grammar EG1, and this is for generating some sentences in the English language. And so a grammar is a finite set of rewrite rules. The first rule of this grammar is this: sentence goes to noun phrase followed by predicate. So a rule is having an LHS and an RHS, and this rule tells us that a sentence is nothing but a noun phrase followed by a predicate. And now, what is a noun phrase? A noun phrase is an article followed by a noun. What's a predicate? The third rule defines a predicate as a verb. And now it defines the rule for article. Article is either A or D. The next two rules defines noun for this grammar, and which is either boy or dog. And the last two rules in this grammar defines verb, is eats or runs. And these words in angular brackets are called variables or non-terminals, and these are like variables in a program. You know that variables are used to hold intermediate values, and finally the values of variables can be used to derive the output. And in the case of a grammar, the variables can be used to derive a string in the language which is known as a sentence. Later we can see. And so these are called variables, and in every grammar, one of the variable must be designated as the start symbol of the grammar, where the derivation of a string starts. Later we can see. So one variable must be designated as the start symbol, and here in this example grammar, sentence is the start symbol. And these words which are not given in angular brackets are called terminals. So terminals are given without angular brackets, and variables or non-terminals are given within angular brackets. And this form of representing the grammar is known as Backus-Naur form, BNF. Now we can see how one can make use of a grammar. That is, deriving a sentence or terminal strings, that is a string of terminal words, is called a sentence. A sentence is a string of terminals, and we can see how can one derive a sentence of string of terminal strings. We can start with the start symbol of the grammar. Okay, because the derivation starts with a variable, and that variable is unique and is called the start symbol. And we know that there is only one rule for the start symbol, and which is the first one. If you apply, you know that you can rewrite the sentence with a noun phrase followed by a predicate, which means a rule like A goes to BC represents the fact that one can replace A with BC. Now we have derived this form, and from there we can try to apply a rule for noun phrase. Now this is the rule for noun phrase. A noun is an article followed by a noun. Predicate is retained as such. Now try to apply a rule for article, and this is the rule applied. An article is replaced with A. Now apply a rule for noun. This is the rule applied. So noun is replaced with boy. Now apply the rule for predicate. Single rule is available. So predicate is replaced with Bob. Now apply a rule for Bob. I applied this rule and now I derived a string of terminal strings, which is known as sentence. A sentence is a terminal string, a string of terminals. So we have seen how a string of terminals known as a sentence can be generated from the start symbol of a grammar by applying 0 or more rules. And the process of obtaining a string of terminals from the start symbol of the grammar is known as derivation. Now the next thing is the language generated by a grammar. For example, what language is generated by example grammar 1? This is an example sentence in the language, and a boy is a sentence derivable from the start symbol of the grammar. So this is a sentence in the language, and a language is the set of all sentences or terminal strings derivable from EG1. The question is, which are all the set of sentences derivable from the start symbol of this grammar? This is a finite language, and if you observe, you can see that these are the set of 8 sentences possible to be derived from the start symbol of this grammar. This is the one that we derived in the example, and if you recall, the last step in the derivation was replacing verb with eats, that is this production. In that place, if you apply this production, then this runs will be, eats will be replaced with runs, and that is the second sentence. Similarly, you can see how all the other strings are derived. If you get time, please try to see how these sentences can be derived. And with this, let us move on to the next example grammar, EG2. So this grammar is not represented in Backus-Naur form, that is angular brackets are not used. From now onwards, we will be using this form for simplicity, where the capital letters represents variables in the grammar. Remember that the variables are also known as non-terminals. So from now onwards, in all the grammars that we are going to see, variables or non-terminals are going to be represented by capital letters. And we know that one of the variable or non-terminal must be designated as the start symbol, and here it is capital A, the start symbol of the grammar. And the small letters are called terminals and are represented by small letters. So in all the grammars that we are going to see, the terminals are going to be small letters. And we know that a string in the language is a string of terminals, also known as sentence. Now we can see the different terminal strings derivable from EG2. We can start with the start symbol, capital A. If you apply production number 1, you know that capital A can be replaced with the RHS of this production, small a followed by capital B. Now if we apply the last production, the B can be replaced with MD string, so B is lost, and hence B can be replaced with epsilon, means you will get only small a. So you derived a terminal string. Now consider deriving the second terminal string. Again, the first production is applied, and that's true, only one production. Production is another name for a rule, okay. Let me use production and rule synonymously, and so a production is also another name for rule, okay. So the first rule is the only rule available for the start symbol, and that is to be applied for deriving any string. So the first rule is applied. Now I apply the rule number 2. So this B should be replaced with RHS of that production. So this B is replaced with small a capital B. Then for this B, I am applying production number 4. So this capital B is replaced with the epsilon, so I am deriving small a. Another example, the first production is applied, so I am getting small a capital B. For this capital B, I am applying production number 3, so I am replacing capital B with small b capital B, and then I am applying the last production, so capital B is replaced with epsilon, so I am deriving small ab. One more example, the first production is applied, I am getting small a capital B. This capital B is now going to be replaced with the second production, so capital B is replaced with small a capital B. Then I am going to apply the production number 2 again for this capital B. So again this capital B will be replaced with small a capital B. And now I am going to apply the last production, that is this capital B is going to be replaced, and hence I am deriving small a. Now the question is, what language is represented by EG2? By looking at the example strings generator, these are the strings generated, can you generalize and say what kind of a string is accepted? The language is this: the set of all strings starting with A. This is how you can mathematically define it. Set of all strings said that A followed by any string of A and B. And intuitively it is correct. And why is it correct? You know that the only one rule available for the start simple is this one. So it must be applied and it generates the first simple as small letter A. Now how can you replace the second simple, that is capital B? If you apply production number 2, this capital B will be replaced with small a capital B. And if you apply production number 3, this capital B will be replaced with small b capital B. That means if you apply production number 2 or 3, this second simple can be either A or B. The first simple must be capital small letter A, the second simple can be either A or B. It tells you that the first simple must be small a and the second simple can be either small a or small b. And production number 2 and 3 can be applied 0 or more times. This star means 0 or more times. So capital B can be replaced with either A or B, meaning the second simple can be either A or B, third simple can be either A or B, and likewise it goes, and hence you can, after the first A, you can derive an arbitrary string of small a and small b, followed by the capital B. And finally, to derive our terminal string, you must have to apply production number 4, and in that case you will replace capital B with the empty string and you derive a string in the form small a followed by x, where x is an arbitrary string, and that is the language. And if you want, you can prove the correctness by using the principle of mathematical induction. So if you recall, the correctness proof involves both the soundness and completeness. Soundness means if I derive a string from the start simple, then that string must start with a small a. That is soundness. And completeness means if you give me any string starting with small a, then that string must be derivable from the start simple using these rules. And that is completeness. And we already have applied the principle of mathematical induction and we discussed it in the class. So please refer to it, and if you get time, please try to prove the correctness using the principle of mathematical induction. And the language is the set of all strings starting with A, and which is a regular language. And why is it that this is regular? Because there exists an N of A for accepting all the strings starting with A. With this, let us move on to the third example grammar, EG3. A set of 3 rules. So what are the different strings possible to be derived? Consider the first case. I am applying production number 3 and I derived a terminal string which is small b. Another example, I applied production number 1, I derived small a capital A. For this A, I am going to apply production number 3, so I derived small ab. Third example, I applied production number 2. Then for this capital A, I am applying production number 3, so I derived small bb. Last example, I applied production number 1, small a capital A. This capital A is going to be replaced with production number 1 again. So capital A is replaced with small a capital A. Again, I have to apply a production for capital A. Now I am applying the last production, and where I replace capital A with small b, so I am deriving small aab. So what language is generated by this grammar? By looking at the 4 strings derived, can you generalize and say what kind of a string is accepted? And the language is the set of all strings ending with B. If you recall, in the previous grammar it was starting with A, and in this case it is ending with B. And intuitively this is correct. Why? Because you can start from the start simple, and you can apply for this A, you can apply production number 1. In that case, the first letter becomes small a. Or you can apply production number 2. In that case, the first letter will be small letter b. So the first letter can be either small a or small b. And the same set of the 2 productions, 1 and 2, can be applied 0 or more times. So the first simple can be small a or small b. Again, the second simple can be small a or small b. Likewise, it goes. If you apply productions 1 and 2, and a production means a rule. Okay, the rules 1 and 2, 0 or more times, you will derive a string of this form. And to derive a terminal string, you have to replace capital A with the last production, and where this capital A will be replaced with small b. So the general form of a string is small x, which is a string of AB followed by B. That is a set of all strings ending in B. Here again, you can use the principle of mathematical induction to prove the soundness and completeness. Try doing it if you are getting time. And you can see that this language is again regular. Why? Because there exists an N of A for accepting any string ending in B. And with this, let us move on to the last example for this lecture, where we have another grammar EG4. Try deriving strings. First case, I am applying production number 1. Now I have to replace this capital B. Let us try to apply the last production. I derived small ba. Second example, only one production is there for the start simple, so I applied it. Now I am going to apply the second production on it. So I am deriving ba followed by capital B. Last production is giving me ba. Third example, I apply production number 1. Now production number 2, apply production number 2 again, and then apply the production number 4. So I am getting ba. So what language is generated? By just looking at the strings generated by these example derivations. Can you tell me what language is generated? In this case, it is easy. It is this language. Set of all ba raised to I, such that I is greater than 0. Then what is the notation ba raised to I? Ba raised to 3 means 3 ba's. Ba raised to 2 means 2 ba's. Ba raised to 1 means 1 ba. So that is the language. And intuitively, it looks correct because you start with the start simple, only one production. So you can derive a string ba followed by capital B. Then capital B can be replaced with production number 2, which gives you this B, small ba capital B. So this is what you get, ba followed by bab. And in fact, you can apply production number 2 0 or more times. If you apply 0 times, then you will get b raised to 0. Okay, because every time this capital B can be replaced with ba followed by b. So the first is ba followed by ba I number of times. If you applied this production I times, followed by capital B. And to derive a terminal string, you have to apply production number 3. And in that case, you will replace capital B with empty string. So you are getting BA followed by BA raised to I, where I is greater than or equal to 0. Because if you apply the second production 0 or more times. And if you combine, you can see that this is exactly BA raised to I, where I is greater than 0. And in this case also, you can use principle of mathematical induction to prove the soundness and completeness and hence the correctness. And if you look at this language, you can see that this language is again a regular language. Why? Because there exists an N of A with epsilon transition for generating this language, BA, any number of times. So in this class, we have seen a new formal representation for a language which is a grammar. And we have seen 4 example grammars, and we saw that the last 3 grammars generated regular languages. Thank you.